Hello, in this lecture we find out the distance between the centers of two circles. In the drawing we have rectangle ABCD. Inside this rectangle we have two circles. The center of this circle is here at point Q, the center of the circle is here at point P. And our mission is to find out the distance between the two centers. That is to say the length of this line segment QP. In addition, we know that side AB of the rectangle is equal to 7 units in its length, and side BC equals to 24 units in its length. Again, our mission is to find out the length of line segment QP, that is the distance between the centers of those two circles. So because of the fact that ABCD is a rectangle, it means that, and we know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to CD. But AB is 7, therefore CD must be also equal to 7 units in its length. And I tell that this side DC or CD is equal to 7 units in its length. According to the sum that the opposite sides of the rectangle are equal to each other, we get that BC equals to AD. But BC is 24, therefore AD must be also equal to 24 units in its length. Because of the fact that ABCD is a rectangle, we know that all the angles inside the rectangle are right angles. So those four angles are all right angles. So this angle equals to 90 degrees. This angle also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle also equals to 90 degrees. Okay, now angle ABC, this angle equals to 90 degrees, therefore triangle ABC is a right triangle. Now we will implement the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, in the right triangle ABC, by PT is a variation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABC is AC, therefore the square of the hypotenuse is AC square. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AB square plus BC square. Repeat again. According to the Pythagoras theorem, in the right triangle ABC, AC square equals to AC square equals to AB square plus BC square. So AC square, that is the square of the hypotenuse, equals to AB square. AB is 7, according to what is given as the question, therefore AB square is 7 squared, that is 49. Plus BC square. BC is 24, therefore BC square is 24 squared, that is actually 576. So, in conclusion, we found out that AC square equals to 49 plus 576, it is actually 625. We take a root out of this equation, and we get that AC equals to the square root of 625, that is actually 25. So actually found out that AC, the length of the hypotenuse AC, is 25 units. Okay. Actually, we have to find out the radius of each circle. In order to find out the radius, those two circles, they are both blocked by a right triangle. This circle is blocked by the right triangle ABC, in this circle it is also blocked by the right triangle CDA. Actually, in the next step we will develop a formula that will help us to find out the radius of any circle that is inscribed, that is blocked by a right triangle. So here we have the right triangle ABC that blocks this circle. We define the radius of this circle as x. And now we will try to find out a general formula that will help us to find out the radius of this circle that is blocked by the right triangle ABC only by knowing the side lengths of this right triangle that blocks the circle. Okay. We have here rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Point O is the center of the circle. The point of tendency of tangent BC with this circle is here, so we define this point as M. M is the point of tendency. So the radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to the radius MO, it means that this angle equals to 90 degrees, and this angle must be also equal to 90 degrees according to rule number 1. We define the point of tendency of tangent AB with this circle as M. We will join points O and N together by a straight line. ON is the radius of this circle that is equal to x according to our definition. The radius ON is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. So inside quadrilateral NOMB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, they must be equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees. So inside quadrilateral NOBM, we have 4 right angles, and therefore we will relate to quadrilateral NOBM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, side OM equals to side NB. But OM equals to x, therefore NB must be also equal to x. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that side NO must be equal to side BM. But NO equals to x, therefore BM must be also equal to x. So we shall find out that quadrilateral NOMB is a square and not a rectangle, because all of its sides are equal to each other. Each of them is equal to x. So what is the length of line segment AN? From the drawing, it is very easy to see that AN equals to AB minus NB. Again, AB minus NB equals to AN. AB is A, and NB is x. So in total, AN equals to A minus x. Here we have rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We define the point of tendency of tangent AC with this circle as S. So from point A, from the common external point A, we have two tangents to this circle, tangent AN and tangent AS. And according to rule number 2, that the lengths of two tangents from a common external point to a circle are equal, we will get that AN must be equal to AS. But AN is A minus x, therefore AS must be also equal to A minus x. BC equals to B units in its length and BM equals to X. BC minus BM is MC. Again, BC minus BM is MC. BC is B and BM is X. So MC must be equal to BC, that is B, minus BM, that is X. So MC equals to B minus X. Here we have also rule number 2. From the counting standpoint, point C, we have two tangents to this circle, tangent CM and tangent CS. And according to rule number 2, they must be equal to each other. That is to say, CM equals to CS. But CM is B minus X, therefore CS must be also equal to B minus X. What is the length of the hypotenuse AC? AC equals to C units in its length according to our definition. But AC also equals to AS plus SC. That is to say, AC equals to in total to AS, that is A minus X, plus SC, that is B minus X. So the hypotenuse C equals to AS plus SC. The length of the hypotenuse is C, and C equals to AS plus SC. So C equals to AS. AS is A minus X plus CS. CS is B minus X. So in total we found out that the length of the hypotenuse C is A minus X plus B minus X. That is to say, C equals to A plus B minus X is minus 2X. We add 2X to this equation and we get that 2X plus C equals to A plus B. We subtract C from this equation and we get that 2X equals to A plus B minus C. So 2X equals to A plus B minus C. We'll divide this equation by 2. And finally we get that X, that is the radius of the circle, equals to A plus B minus C over 2. So in this way we actually created a general formula that will help us to find out the radius of any circle that is blocked by a right angle. The radius of this circle X will be equal to A plus B minus C over 2. Okay, I'll repeat again. The radius of this circle, that is X, the length of X must be equal to A plus B, that is the sum of the lengths of the side lengths of this right angle, A plus B, minus the length of the hypotenuse, that is C, over 2. Now we'll use this formula in order to find out the radius of our two circles. So here we have this circle. This circle is inscribed or is blocked by the right triangle ABC. So we use the new formula in order to find out the radius of this circle. Repeat again, we'll use the new formula in order to find out the radius of this circle that is blocked by the right triangle ABC. According to the new formula, we define the radius of this circle as R, and according to the new formula, R equals to A plus B minus C over 2. So the radius of this circle that is blocked by the right triangle ABC equals to A. A is equals to 7 units in its length, plus B. B is 24 units in its length, minus the length of the hypotenuse AC that is 25 over 2. So the radius of this circle R must be equal to 7 plus 24 minus 25. 7 plus 24 is 31, and 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that the radius of this circle R is equal to 3 units. We define the point of tendency of tangent BC with this circle as point M. According to rule number 1, the radius PM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MP. If BC is perpendicular to the radius MP, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. We define the point of tendency of tangent AB with this circle as N. We join points P and N together by a straight line. Pn is the radius of the circle that is equal to 3 units. The radius Pn is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees. So inside quadrilateral NPMB, inside this quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of this fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees. In order to complete the sum of the angles inside this quadrilateral to 360 degrees, the missing angle must be equal to 90 degrees. So inside quadrilateral NPBM, we have 1, 2, 3, 4 right angles, and therefore we relate to quadrilateral NPBM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, NC equals to BM, but NP equals to BM. But NP is 3, therefore BM must be also equal to 3. Likewise, in the same rectangle NPBM, side PM must be equal to side NB. Repeat again. Side PM must be equal to side NB. But PM is 3, therefore MB must be also equal to 3 units in its length. So actually found out that quadrilateral NPBM is not a rectangle but a square, because all of its sides are equal to each other, they are equal to 3 units. Each of them is equal to 3 units. We repeat on the same process on the other circle, the right circle here. We define the point of tendency of tangent AD with this circle as point G. We join points Q and G together by a straight line. QG is the radius of the circle. So we will find out the radius of the circle. According to the new formula, the radius will be equal to CD, that is 7, plus AD, that is 24, minus the length of the hypotenuse AC, that is 25 over 2. Again, that the radius of the right circle must be equal to 7 plus 24, that is 31. 31 minus 25 is 6, and 6 over 2 is 3. So I found out that the radius of this circle is also equals to 3 units. Okay, so QG equals to 3 units. So the radius QG is drawn to point G, that is the point of tendency of tangent AD with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AD must be perpendicular to the radius GQ. That is to say, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule number 1. We define the point of tendency of tangent DC with this circle as J. We join points Q and J together by a straight line. QJ is the radius of this circle, that is equal to 3 units. The radius QJ is drawn to point J, that is the point of tendency of tangent DC with this circle, and whenever a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius JQ. If this is perpendicular to JQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. So inside quadrangle QJDG we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. Therefore we can relate to quadrangle QGDJ as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, QJ equals to GD. But QJ is 3, therefore GD must be also equal to 3. The same rectangle GQJD, side GQ must be equal to the opposite side DJ, but GQ is 3, therefore DJ must be also equal to 3 units in its length. So actually we found out that quadrangle GDJQ is not a rectangle but a square, because all of its sides are equal to each other. Each of them is equal to 3 units. Okay, so we have here 2 squares, 2 identical squares. In the next step, we will extend the radius NP until it touches side DC of this rectangle ABCD. Again, we will extend the radius NP by a straight line until it will touch side DC of rectangle ABCD. The radius NP is a straight line, and we extended the straight line NP by a straight line, therefore the result is a straight line. So we define the touching point of the extended NP with this circle as T. So NT is a straight line, because when you extend a straight line by a straight line, the result is a straight line. So NT is a straight line. So actually in this way we created quadrangle NBTC. Inside this quadrangle NBTC we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. So we can relate to quadrangle NTCB as a rectangle because it has 4 right angles. Okay? And we know that the opposite sides of a rectangle are equal to each other. That is to say, NB equals to TC. But NB is 3, therefore TC must be also equal to 3 units. In the same rectangle, NTCB, side BC must be equal to the opposite side NT. But BC is 24, therefore NT must be also equal to 24 units in its length. NT must be equal to 24 units. We will extend the radius GQ by straight line until it will touch side BC of rectangle ABCD. Again, GQ is a radius is a straight line. When you extend a straight line by straight line, the result must be a straight line. So here we define the touching point of the extended radius GQ and side BC as point H. So inside the quadrilateral HCDG we have 1, 2, 3 right angles, therefore this fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay. So we define the intersection point here is point F. Inside quadrilateral FTCH we have 1, 2, 3 right angles, therefore this fourth angle must be also equal to 90 degrees. DC is one side of rectangle ABCD, therefore it is absolutely a straight line. So if we focus on this side of the straight line DC, at point T, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have this side of the straight line DC at point T? We have this angle that is equal to 90 degrees, plus the missing angle. In total they must be equal to 180 degrees, according to the rule that I mentioned. Therefore, the missing angle must be equal to 90 degrees. In order to complete the sum of the angles on this side of the straight line DC at point T to 180 degrees, this missing angle must be equal to 90 degrees. GH is a straight line because when you extend the radius GQ by straight line, the result is GH that must be also a straight line. So if you focus on this side of the straight line GH at point F, the sum of the angles here must be equal to 180 degrees. So which angles we have this side of GH at point F? We have this angle that is equal to 90 degrees, plus the missing angle in total must be equal to 180 degrees, according to the rule that I mentioned. Therefore, the missing angle must be equal to 90 degrees. Likewise, we'll focus on this side of the straight line DC at point J. So, okay, so this angle equals to 90 degrees. We've already found out that this angle equals to 90 degrees. Anyway, at this side of the straight line DC at point J, this angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees. Likewise, if you focus on this side of the straight line GH at point Q, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of the straight line GH at point Q? We have this angle that is equal to 90 degrees, plus the missing angle here. In total they must be equal to 180 degrees, therefore the missing angle must be equal to 90 degrees. So inside quadrilateral QJTF, we have 1, 2, 3, 4 right angles. Therefore, we can relate to quadrilateral QJTF as a rectangle. We know that in total, DC equals to 7 units in its length. Therefore, DC minus DJ minus TC, so DC minus DJ minus TC must be equal to JT. Again, DC minus dj minus tc must be equal to the missing side jt. So dc is 7 minus dj is 3 minus tc, that is also 3. So the missing side here, jt, equals to 7 minus 3 minus 3. 7 minus 3 minus 3 is 1. In conclusion, we found out that the length of jt is 1 unit. And we know that the opposite sides of a rectangle are equal to each other. So in rectangle QJTF, side JT must be equal to side QF. But JT is 1, therefore QF must be also equal to 1 unit. Here we extended the radius NP, that is of course a straight line, absolutely a straight line, by straight line, and we got NT. When you extend the straight line by straight line, the result must be a straight line, so NT is a straight line. If we focus on this side of the straight line NT at point F, here the sum of the angles must be equal to 180 degrees. So which angles we have at this side of the straight line NT at point F? We have this angle that is equal to 90 degrees, plus the missing angle here. In total, they must be equal to 180 degrees. I'll repeat again. At the upper side of the straight line NT at point F, the sum of the angles must be equal to 180 degrees. So 90 degrees plus the missing angle, in total they must be equal to 180 degrees. Therefore, the missing angle here must be equal to 90 degrees. Okay. Here also, NT is a straight line, so if you focus on the lower side of the straight line NT at point P, the sum of the angles must be equal to 180 degrees according to the same rule. So which angles we have at the straight line, at the lower side of the straight line NT at point P? We have this angle that is equal to 90 degrees plus the missing angle. In total, it must be equal to 180 degrees. Therefore, the missing angle here must be equal to 90 degrees. So inside quadrilateral PFMH, we have 1, 2, 3 angles. Therefore, the fourth angle must be equal to 90 degrees. Therefore, quadrilateral PFHM, this quadrilateral that has 4 angles, will relate to quadrilateral PFHF as a rectangle. We relate to quadrilateral PFHM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, PF equals to MH. But what is the length of PM? What is the length of PF? PF equals to NT. First of all, NBCT is a rectangle because quadrilateral NBCT has 1, 2, 3, 4 right angles. And you know that the opposite sides of a rectangle are equal to each other. That is to say, BC equals to NT. But BC is 24, therefore NT is also 24. NT is 24 units. So NT that is 24 minus NP minus FT must be equal to PF. Again, NT that is 24 minus NP minus FT, in total it must be equal to PF. Again, NT minus NP minus FT must be equal to PF. So NT is 24. I will write it down. NT minus NP minus FT it must be equal to the missing side PF. So first of all, inside the quadrilateral PTHC we have 1, 2, 3, 4 right angles. Therefore we can relate to quadrilateral FTCH as a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, TC equals to FH, but TC is 3, therefore FH must be also equal to 3 units. We already found out that GDCH is a rectangle. The big quadrangle GDCH is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, GD equals to HC. But GD is 3, therefore SC must be also equal to 3. And because of the fact that inside quadrangle PTCH we have 1, 2, 3, 4 right angles, we can relate quadrangle FTHC as a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, HC equals to FT, but HC is 3, therefore FT must be also equal to 3. In conclusion, we found out that FT equals to 3 units. So NT is 24 minus NP, that is 3, minus PT minus, actually it is FT. NT is 24 minus NP, that is 3, minus FT minus FT. FT is 3. It must be equal to the missing side PF. So PF equals to 24 minus 3 is 21, and 21 minus 3 is 18. So PF equals to 18 units in its length. This side PF equals to 18 units in its length. Inside quadrangle PFMT, PFMH. Again, inside quadrangle PFMH, we have 1, 2, 3, 4 right angles. Therefore, we can relate to quadrangle PFMH as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle PFMH, side PF must be equal to the opposite side MH. But PF is 18, therefore MH must be also equal to 18 units in its length. Anyway, side PF equals to 18 units, side QF equals to 1 unit. In the next step, we'll implement the Pythagorean, and this angle QFP equals to 90 degrees, according to what we have already found out, according to the rule that the sum of the angles on one side of a circle is equal to 180 degrees. This angle equals to 90 degrees. In the next step, we'll implement the Pythagoras theorem in the right green triangle, triangle PFQ. So I'll copy the right green triangle PFQ in a new page, and we'll implement on it the Pythagoras theorem. So actually, this is the right triangle QPF that I copied from the original drawing. In the next step, we will implement on this right triangle the Pythagoras theorem. By PT is the abbreviation for Pythagoras theorem. So in the right triangle QPF, according to the Pythagoras theorem, QP square equals to QF square plus PF square. Write it down. QP square, that is the square of the hypotenuse, equals to QF square plus PF square. So QP square equals to QF square. QF is 1, therefore QF square is 1 square. That is 1 plus PF square. PF is 18, therefore PF square is 18 squared, that is 324. So QP square equals to 324 plus 1 is 325. We take a root out of this equation and we get that QP equals to the square root of 325 QP equals to the square root of 325. 325 is 25 times 13. You can take out 25 out of the root. The square root of 25 is 5. And you get that QP equals to 5. Inside the root we left only 13. So actually found out that the answer to this question, that the length of this line segment QP, that is the distance between the centers of those two circles, is equals to either to 5 times root of 13 units, or in terms of numbers is 18.03 units. That is the answer to the question. In the next step, I'll summarize the lecture. So in this lecture we found out the distance between the centers of those two circles, that is to say, the length of this line segment QP. Again, the center of this circle is 0 at point Q, the center of this circle is 0 at point P. We have to find out the distance between the two centers of those two circles, that is to say, the length of this line segment QP. So, those two circles are located inside rectangle ABCD. We know that the width of the rectangle is equal to 7 units and the length of this rectangle ABCD is 24 units. Again, our mission is to find out the distance between the centers of those two circles, so in other words, the length of this line segment QP. First of all, because of the fact that ABCD is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DC, but AB is 7, therefore DC must be also equal to 7 units in its length. According to the same rule, AD must be equal to BC, but BC is 24, therefore AD must be also equal to 24 units in its length. Because of the fact that ABCD is a rectangle, it means that all the angles inside the rectangle must be right angles, so those 4 angles are all right angles. And because of the fact that ABC, this angle ABC equals to 90 degrees, it means that triangle ABC is a right angle, therefore we can implement the Pythagoras theorem on the right triangle ABC. According to the Pythagoras theorem in the right triangle ABC, AC square equals to AB square plus BC square. Repeat again. In the right triangle ABC, AC square equals to AB square plus BC square. So AC square, that is the square of the hypotenuse, equals to AC square. AC is 7, therefore AC square is 7 squared, that is 49. Plus BC square. BC is 24, therefore BC square is 24 squared, that is 576. So we can find out that AC square equals to 49 plus 576, that is 625. AC square equals to 625. We took out of this equation and finally found out that AC equals to the square root of 625, that is 25. So the length of the hypotenuse AC of the right triangle ABC is 25 units. Okay. Then, so here we have this circle is blocked by the right triangle ABC, and this circle is also blocked by the right triangle CDA. Then we actually developed a formula that will help us to find out the radius of any circle that is blocked by the right triangle. Triangle ABC is the right triangle because this angle equals to 90 degrees. The right triangle ABC blocks this circle. We know that the length of side AB is A units, side BC equals to B units in this length, and the length of the hypotenuse of the right triangle ABC, AC equals to C units in its length. We defined the radius of this circle as X. Point O is the center of the circle. So we developed a new formula that will help us to find out the radius of this circle, that is to say the value of X, only by knowing the side lengths of the right triangle that blocks this circle. So here we define the point of tendency of tangent BC with this circle as M. We join points O and M together by side line OM is the radius of this circle that is X. The radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. We define the point of tendency of tangent AB with this circle as N. We join points O and N together by side line. ON is the radius of the circle that is equal to X. The radius ON is drawn to point N. The radius ON that is X actually is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees. So inside quadrangle ONBM, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. So inside quadrangle NOMB we have 4 right angles, therefore we can relate to quadrangle NOBM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other, that is to say NO equals to BM. But NO is X, therefore BM must be also equal to X. Likewise, according to the sum rule, that the opposite sides of a rectangle are equal to each other, we get that OM equals to NB. But OM is X, therefore NB must be also equal to X. So actually found out that quadrangle NOMB is not a rectangle but a square because all of its sides are equal to each other, each of them is equal to X. So AB minus NB is AN. Again, AB minus NB is AN. AB is A and NB is X. So in total AN must be equal to A minus X. Here we have rule number 2. If you focus on the common example point A, from the common example point A, we have 2 tangents to the circle, tangent AN and tangent AS. And according to rule number 2, they must be equal to each other. Rule number 2 states that the lengths of those of 2 tangents from a common example point to a circle are equal. From the common example point A, we have 2 tangents to the circle, tangent AN and tangent AS. According to rule number 2, they must be equal to each other. That is to say, AN equals to AX. AN equals to AS. But AN is A minus X, therefore AS must be also equal to A minus X. So what is the length of right segment MC? It is very easy to see from the drawing that MC equals to CB minus CM. Again, CB minus CM equals to, again, CB minus BM is MC. Again, CB minus BM is MC. CB is B and BM is X. Therefore, in total, CM equals to B minus X. B minus X is CM. So, CM or MC is B minus X. If we focus on the common example point C, from the common example point C, we have 2 tangents to the circle, tangent CM and tangent CS. And according to rule number 2, they must be equal to each other. That is to say, CM equals to CS. but Cm is b minus x, therefore Cs must be also equal to b minus x. Okay? So the length of the hypotenuse AC of the right angle ABC is C, but the length also equals to AS plus SC. AS is A minus X and SC is B minus X. So in total, AC must be equal to A minus X plus B minus X. Okay, so here the length of the hypotenuse is C, and C equals to AS plus CS. AS is A minus X and CS is B minus X. So in total, C equals to A minus X plus B minus X. A minus X plus B minus X is A plus B minus 2X. We subtracted, we added the 2X to this equation and found out that 2X plus C equals to A plus B. We subtracted C from this equation and found out that 2x equals to A plus B minus C. We divided this equation by 2 and finally found out that x equals to A plus B minus C over 2. That is to say, the radius of this circle, that is x, it must be equal to A plus B minus C over 2. And this is the general formula for finding out the radius of any circle that is blocked by a right triangle. Because triangle ABC is a right triangle. We can use this formula in order to find out the radius, the radii of those two circles, because those two circles, they are both blocked by the right triangle. This circle is blocked by the right triangle ABC, and this circle is also blocked by the right triangle CDA. So we use this formula in order to find out the radius of those two circles, the radii of those two circles. The radius of this circle, R, it must be equal to A plus B minus C over 2. I'll repeat again. The radius of the left circle equals to A plus B minus C over 2. A is 7, B is 24, and the hypotenuse C is 25. All divided by 2. So 7 plus 24 is 31. 31 minus 25 is 6. 6 over 2 is 3. So we found out that the radius of the left circle equals to 3 units in its length. Then we found out the radius of the right circle. According to the same formula, R equals to A plus B minus C over 2. R is 7, B is 24, minus C, that is 25 over 2. 7 plus 24 is 31, 31 minus 25 is 6, and 6 over 2 is 3. So we shall find out the radius of this circle is also equal to 3 units in its length. And then we found out we extended, first of all, we have here we join points P and M together by a straight line. PM is the radius of this circle is equal to 3 units. According to rule number 1, this angle equals to 90 degrees and this angle equals to 90 degrees. We join points P and N together by a straight line. According to rule number 1, this angle equals to 90 degrees and this angle equals to 90 degrees. So inside quadrilateral NPBM, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. Therefore, quadrilateral NPBM is a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, NP equals to BM, but NP is 3, therefore BM must be also equal to 3. Likewise, according to the same rule, PM equals to NB, but PM is 3, therefore NB also equals to 3. We repeated the same process here. So, quadrilateral NPBM is a square because all of its sides are equal to each other. Each of them is equal to 3 units. We repeated on the same process here. And we actually found out that QJDG is also a square. So we have here 2 squares. Then we extended the radius NP by a straight line. So in this way until it touches the side DC at point T. inside quadrilateral NBCT we have 1, 2, 3 right angles. This angle equals to 90 degrees because ABCD is a rectangle. So we have inside quadrilateral NBCT 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. So inside quadrilateral NTBC we have 4 right angles, therefore we can relate to quadrilateral NBCT is a rectangle, and you know that the opposite sides of a rectangle are equal to each other. That is to say NB equals to TC, but NB is 3, therefore TC must be also equal to 3 units. So here we have 1, 2, and here this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees. This angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees because NT is one straight line. Then we extended the radius GQ until it touches side BC point edge. In this way, created quadrilateral GDCH. Inside this quadrilateral, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. Okay, so inside quadrilateral FTCH, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So inside quadrilateral FTCH we have 4 right angles, and we know that, so we can relate to quadrilateral FTHC as a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say TC equals to FH, but TC is 3, therefore FH must be also equal to 3. So, and inside this quadrilateral, this rectangle GDCH, GD must be equal to HC, but GD is 3, therefore HC must be also equal to 3 units. And here also in rectangle FTHC, HC must be equal to FT, but HC is 3, therefore FT must be also equal to 3 units in its length. And you also know that FH also equals to 3 units in its length because FTHC is a rectangle. Actually, now we found out that it is not a rectangle but a square because all of its sides are equal to each other. So this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees. So here we have FP edge M is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say M edge equals to PF. What is the length of M edge? M edge equals to BC, that is 24, minus 3 minus 3. That is to say M edge equals to in total to 24 minus 6, that is 18. So in rectangle PF M edge equals to PF. But M edge is 18, therefore PF must be also equal to 18 units in its length. This angle equals to 90 degrees, and G edge is a straight line. So if you focus on this side of the straight line G edge at point F, the sum of the angles must be equal to 180 degrees. Therefore the missing angle must be equal to 90 degrees. We have already found out that QJTF is a rectangle because we have 2, 4 right angles inside quadrilateral QJFT. Therefore QJFT is a rectangle, and you know that the opposite sides of a rectangle are equal to each other. That is to say JT equals to QF. What is the length of JT? JT equals to DC, that is 7 minus 3 minus 3. 7 minus 3 minus 3 is 1. So JT equals to 1 unit. So in rectangle QJTF, JT equals to QF. But JT is 1, therefore QF must be also equal to 1 unit. Okay. Then I copied the right green triangle QPF in a new page. This is the right triangle QFP that I copied from the original drawing. Side QF equals to 1 unit in its length. side PF equals to 18 units in itself, and the only missing side is the side of the hypotenuse QF. According to the Pythagoras theorem, in this right triangle QPF, QP square equals to QF square plus PF square. So QP square, that is the square of the hypotenuse, equals to QF square. QF is 1, therefore QF square is 1 square, that is 1, plus PF square. PF is 18, therefore PF square is 18 square, that is 324. So in conclusion, found out that QP square, that is the square of the hypotenuse, equals to 324 plus 1 is 325. We took a root out of this equation and finally found out that QP equals to the square root of 325. 325 is 25 plus 13. So we substitute 325 by 25 plus times 13. And the square root of 25 is 5. So we can take out of the root 25. And we get that, again, the square root of 25 is 5. So inside the root we left only with 13. So in conclusion, we found out that the length of line segment QP, or the distance between the centers of those two circles, that is the length of line segment QP, it is equal to either 5 times square root of 13 units, or in terms of numbers, it is equal to 18.03 units. Okay, thank you very much.